Dirac spin equation. Then you actually expect this, if you force yourself to use this two zero flat states to do the neural simulation, then you actually expect the energy density to be degenerate, because you are sort of using the descendant state to simulate the problem, and they both can very well approximate the parent state. So of course, there's a lot of future work that one actually do. But let me now move on to some SPT physics. But here I try to demonstrate some very practical application of this machinery.
Sorry, I need some basic point. How do we get the energy?
You have to, for these different classes, you do all energy optimization separately.
Yeah. And when you calculate the energy, you don't need further RT.
Oh, your maximum technical detail. That's it's like a single layered Tensor RG together with measuring of the color. That's how we measure it. How we measure it.
So the energy itself is not the exact energy density.
Yeah, of course. There's some approximation introduced. That's why you have to do this extrapolation. But you have to, but you also always have to keep a finite cut.
How big is the system size?
Sorry, 8 by 3.
8 by 3. That's not very big.
That's not very big. That's right. Yeah, we also did some some ITEPD measurement, which I can present you later. Or whose result is roughly consistent with this finite sense result.
But that's also not accurate because the infinite size.
Yeah, so yeah, we can talk about that. So all different algorithm has some advantage and disadvantage. Okay, so now let's talk about this SPT. So I don't have too much time, but so remember yesterday I was claiming this result. You can put in SG being the full symmetric group, and in this spatial dimension classify some partially classified bosonic SPT. And but you have to keep in mind T and P should be treated as anti-unitary. So yesterday we talked about this one-dimensional example, but you can also directly apply this result to higher dimensions. You can get some classification of topological phase. For example, if you have both transversal and mirror symmetry in two spatial dimensions, it tells you that you have 4 different SPT phases. So one of them is trivial, so you have 3 non-trivial SPT phases in 2D. So you can, of course, work on other examples. And for every one of these such a phase, you can construct generic wave function, very similar to what we did for the cognitive case. But here is a SPT which does not have a topological order. So here, remember, SET has topological order, SPT does not have topological order. So if I have time, I also mention there's a general connection between SET and SPT in 2D. So let's come back to this two-dimensional lattice, and let's again try to identify this IgG. So remember, this IgG play a very important role in one dimension to get this SPT phases. Right? In 2D, the reason why in 1D I only have one global phase is that there's only like one loop in one dimension. If I have a chi, then chi star, another chi star, so only one loop. But for example, think about the square lattice. For every plaquette, you have a loop. For every plaquette, you can imagine you apply these phases, chi inverse, chi inverse around the loop, and this leaves all the tensor completely there. Then this is the gauge transformation. So for every plaquette, there's a phase belong to IgG. And for different plaquette, you have a different phase. You could have different phases. There's an infinite number of phases. Right? So it looks more complicated. But what's turned out to be even more subtle is in order to describe these strong SPT phases, you actually have to generalize this chi phase into some matrices. So namely, you need to assume the tensor network have a larger invariance. So every tensor network would satisfy this kind of invariance. But if these lambdas are matrices, then this tensor have to be rather special to satisfy this invariance, because I will require, for example, this tensor to be invariant under this lambda L inverse here and the lambda D there. So you have to live with some subfields. But it turned out that I need this in order to describe strong SPT phases. Again, remember, I have many plaquettes. So what you really should imagine is for every plaquette, there's such kind of IgG, a matrix IgG. Yeah, so you can imagine that they are different. So in fact, to describe strong SPT, you generally require them to be different.
But why did you start with something the same there for all four phases?
Oh, because I need this tensor to be completely invariant. So if I multiply chi here, have to be chi inverse.
But then the four.
But the here is different. This is our matrices. Right? Yeah. So I will give you some physical interpretation in a moment. But at this moment, let me just directly give you how the way to construct this SPT using tensor. So in order to describe this homology SPT, we assume any global matrix IgG. Think about the J. This J is global. I multiply J everywhere on the virtual lab. In the previous example on the carbon lattice. So we will require this J invariance can be decomposed into this product of this matrix IgG. This product is a plaquette matrix IgG. The P means plaquette, and then you multiply all this. You multiply all this, then you can get this global IgG. That's the assumption. And
these lambda are matrices.
lambda are also matrix.
So there is an order we multiply.
It turned out that if you assume under, of course, there's some assumption under this, and basically under this assumption, you can show that this lambda has to complete. But somehow it's three dimension. This no longer has to be true. So there's a physical interpretation. The physical interpretation is if this J cannot be decomposed, if you have some global IgG also from the matrix, but cannot be decomposed as this plaquette IgG, then you can show, as I mentioned, you generally have to be topological order, because you can construct different ground state. So this is not equal to that. But it turns out that if you can decompose this into this plaquette IgG, then you can show this equals that. So physically, it actually tells you that this J stream are condensed after you require this extra plaquette IgG. Okay. So the topological order actually is destroyed. But so here you can see technically. So I will explain the physical meaning in a moment. But technically, you can see that when I try to decompose this J into product of this lambda, there's a phase ambiguity. And the reason is, for example, I can decompose this J in this way, but I can equally find to redefine this lambda by combine this original plaquette lambda with this phase chi star. I multiply this lambda p by this chi star. It's equally is certainly another plaquette IgG, and the product of this plaquette IgG will give you the same J as before. And if you look at this, over the whole lattice, there's only one phase ambiguity. If you fix this chi phase in one plaquette, you fix this chi everywhere because you want to maintain this decomposition. So you want to maintain the product equal to the original J. So then there's only one phase ambiguity. And it turned out that this phase ambiguity will give you this third cohomology. So related to this spherical cycle, which was briefly mentioned in Jonah's talk. So the basic strategy to construct two-dimensional SPT is the following. So as I mentioned, so this is very similar to one-dimensional case. So WG don't have to be representation, so they can differ by this IgG element. This eta is some global IgG. The global IgG has to satisfy this associativity condition. And this global IgG, we assume it can always be decomposed into the plaquette IgG.
What's the meaning that WG1?
This group action. Sorry. So this is whenever when I write something like a G1 on some W, sorry, maybe some eta. In this case, it means just a G1 eta combination. Similarly for WG. So this is the consequence of associativity. So we assume all the eta can be decomposed into plaquette IgG. So then we can decompose this eta separately. But then after the decomposition, you compare the both sides. The both sides don't have to be equal because, as I mentioned, when you do the decomposition, there's a global phase ambiguity. There's a chi ambiguity over the whole lattice. So this will turn out to be a spherical cycle. So which is a mathematical object, which I don't have time to explain. But here maybe the highlight is the following. This chi, in this formulation, it's obvious how this chi, how symmetry acts on this chi. For example, if you do translation or rotation, chi go to chi. Or for usual onset symmetry, chi also go to chi. If you do time reversal, chi go to chi star. But here, you can for the mirror symmetry, you can convince yourself no matter you do the mirror here or there, chi always go to chi star. So just like time reversal, mirror send chi to chi star. So it should be treated as NG integer. So you can construct different examples, which I'm planning to talk about this example, but maybe I don't have enough time. But maybe let me firstly go through, and then I can maybe spend some time talk about this example. So the point is, for this SPT phases, you can do something similar as this Kagome example that I mentioned. You can firstly classify different classes of tensors. They describe different SPT. And for every class, you can solve the tensor equation if you fix the bound dimension. You can solve it algebraically, and then for every fixed bound dimension, you can solve all the symmetrical transformations. And then you can constrain your subcategory space, which turn out to be useful to do numerical simulations. And the similar construction can be generalized to 3D dimension. But the algebra becomes quite different. But eventually you can show that in 3D dimension this also works. And again, time reversal and mirror should be treated as anti-unit. But the translation rotation should be unitary. Okay. So maybe I'll try to spend the remaining time to explain this example. Actually, I probably have 2 minutes, 3 minutes. Okay. I probably have enough time. So I will give you an example on the square lattice. And so according to this according to this condition, I need this. Suppose I try to construct this D2 SPT. I want to find those lambdas and the WGs so that this chi correspond to this non-trivial SPT. Turn out for this symmetry group into eigensymmetry. And this to realize the circle cycle for the SPT, non-trivial SPT. The only non-trivial chi is this GGG equal minus 1. All other plus 1. Okay. And so what happens is the important, so eventually to realize this tensor equation, what it means is you want your WG, G is the eigensymmetry, the WG square equals some J, and this J is decomposable into product of these lambdas. So, and you want this J to be a product of these lambdas. And you need this, it turned out that to realize this, what you actually require is this WG act on this lambda t equal minus lambda. So think about this. Think about you have some lambda left inverse, lambda left, and so on, some lambda down, inverse. So basically you have to so if you find this WG and the J and the lambda t satisfy these equations, then you realize this SPT. And you can solve this, this equation for different bound dimension. But here, maybe I want to highlight the physical meaning of these equations. So remember, if this J is not decomposable, I actually have a topological order state. So namely, I can create a J string. I can multiply J and J over string, and I create some n particle here. But if this J is decomposable in this way, actually it really means that I can create this n particle without costing any energy. So it means I can, so this J by definition is product of some lambda here and some lambda there. So it's a lambda right, and some lambda left inverse on the other side, and some lambda right inverse. And so if I put some lambda down inverse here, so by this this invariance condition, it turned out that you can show this J string together with some lambda down on the bottom don't cause you don't even modify the wave function. So you create an m particle, but you are not modifying the wave function. It physically means your m particle is condensed. And here, this equation tells you that if you have a WG act on this lambda, you will pick up some minus sign. So physically, it means you have an m condensate, the m particle condensate, and the condensed m particle under the symmetry transformation is icing odd. It's a pick up minus sign, icing odd. So this is related to the onion condensation mechanism, which I mentioned earlier, which turned out to be quite general. So you condense this m in the Z2 topological phase. You suppose initially your J is not decomposable, but you condense this m by requiring this. And if the condensed m carry icing odd quantum number, you get an SPT. So that's the end of story. So sorry. it's just you know, the high-dimensional topological order is more complicated.
Already condense memory.
Yeah, you do need that. But you know, we do know how to. So in three dimension we have a similar kind of tensor equations. But it's no longer only plaquette. You have some volume and also plaquette. So all of them are there.
So it's like a 3-layer cake.
Yeah, you have a 3-layer. And your question is what's the physical interpretation of this 3-layer? And that we haven't worked on yet.
So going back to this variational translation conglomeratics, it's been always said that energy is just a short-range quantity. So if you want to lower it, you can do rather well, even if you are making totally wrong thing for the infrared thing. So I think that's reasonable. But in your case, so you have lots of control parameters, variational parameters, but you are sort of doing well for only 2 of them, and you are rather off for the other cases. How should I understand this?
For the other cases, because you mean the 2 other states?
You had several candidates, but only 2 of them are unique.
Yeah, so that's sort of expected. You don't expect they all doing well, because the whole purpose is to separate them.
Of course, of course it works okay, but do you understand why? Because if you have sufficiently many parameters, then it looks like you can lower variational energy.
Okay. No, the answer is no. So that's why we do this in this way. So we, if say I'm in the true ground state is some 0 flat state, but I force myself to use pi flat state to do simulation. Then the optimal energy density for the pi flat state will be bounded. You can never. So that in this way I can separate.
It's a sort of local constraint.
Yeah. So that's what exactly right. So the constraint on the tensor is very local. Energy density is also very local. So that's sort of expected.
Is there a reason? So when you say the JE is the global IDG is the product of the plaquette.
Right.
Is there a reason why the plaquette is shorter?
This is a big. I think this is a big. This artifact of the tensor construction. Even you can ask even for J, right? So suppose I try to describe topological order, little topological order. So why do I need some Z2 matrix J on a single leg, right? So I could have some emergent, some little dynamics which is invisible on a single leg. Right? So, but if I require, I can see that on a single leg, I have a J, similar for the plaquette. So if I require myself to see this SPT physics on a local, very local, then I have to pick up this plaquette. But it's true, physically you could imagine this onion condensation happen somehow. It's invisible on a single plaquette.
You mean that compared to a Gaussian tensor,
That is for sure.
So for this tensor as topology, actually it's defined on due type analysis on the you consider this tensor, Java, they use some due length function.
I'm not using that. I'm using the original company.
It's a rank 4.
Rank 4. Rank 5. Actually.
Yeah, they use rank 3.
They use they have some star and some different. We are doing a different geometry.
I'm wondering you can also consider U1 state or not.
U1 state. Okay, good question.
That you want to parent state.
Yeah, I certainly can implement some U1 IDG here, but I think the physics of this U1 IDG may or may not be the related to the U1 Dirac IgG. So because this is a sort of
maybe you use some like grass now for that.
yeah, so then I totally agree. Yeah, I totally agree.
I missed the point why beta has to be decomposed into automatic IgG.
Yeah, because if the global IgG is not decomposable, it is some matrix generally. If it's not decomposable, then you have to order. So you want this decomposition condition helps you that to destroy the topological order. Because I'm talking about SPT. Yeah, so you condense some anion, carry all the quantum number. That's the idea.
Okay, for quantum lattice. So, is there anything that numerical people can do for you to distinguish between these two possibilities? Measuring something else?
Yeah, that's a very, very good question. So certainly, so the direct evidence, I would say, would be to directly compute the excitation spectrum. That's because your Dirac is a pretty strong claim, right? It tells you the low energy excitation has some Dirac-like spin down, and we try to do that. And actually, recently there's some work using the DMRG algorithm, but they compute I think the eigenvalue of the transfer matrix. I think it's related to the excitation spectrum, but may not be identical. So I would really try to compute the excitation spectrum, directly compute the excitation spectrum of the spin down. And if I see this Dirac, then it's pretty strong.